Okay, then today, so basically in quantum mechanics, we have, maybe we can call this review. So in quantum mechanics, the main object you're working with is a wave function, which could be a function of position and time, and position could be in 3D, but we start with 1D. Then from this wave function, you need first of all extract some information. So to extract information, you can calculate some probabilities. So that then the probability to find particle around point x at time t would be wave function absolute value square. Yeah? This is the density of probability, so you have to multiply it by volume. In 1D, this is just the element on the length. Then you can extract some average values. One of possible examples would be x, average position, and then this is where you start to have operators. So average position is kind of obvious, but then average momentum, it's a little bit less obvious. Yeah? So you have an operator which you apply to the right on the wave function and dx. And then you have basically operators to extract useful information. So this would be addition to the wave function. A couple of standard operators is position, and position is just multiplication by x, and the operator of momentum, which is less trivial. Yes, you would agree with this. But we also have other operators. Energy, for example, I h bar d over dt. We can calculate Hamiltonian, which is operator p square over 2m plus potential energy as a function of x. So then you have a bunch of operators which corresponds to some physical quantities. And then you can calculate expectation values from them. Yeah? And there is another part of quantum mechanics. How can you find this wave function or equation, like Schrödinger equation? And last time we were talking about time-dependent Schrödinger equation. Basically, operator h applied to the wave function. And this is time-dependent, yeah? And we have a stationary or time-independent Schrödinger equation. If you say that my wave function is eigenvector of energy operator, so I can take the left side of this equation and replace with some number multiplied by the same function, then you would call this stationary solution. Then your Schrödinger equation will change into time-independent Schrödinger equation. So then there are two different directions in which we can go. One direction, we can focus on Schrödinger equations and try to learn how to solve the Schrödinger equation. Different types, stationary, time-independent, and time-dependent, both of them. And there is a lot of skills required to do this because it's a differential equation, partial derivatives, second order. So it could be very complicated, especially if you go to 2D or 3D, like hydrogen atom, for example. But this probably is the most interesting, because as a result of this solution, you're going to get energy and the possible wave function, possible states. The second direction, we can focus on these expectation values and also on these operators. So what can we do with these operators? Can we do something about these operators? And actually, there is something we can call algebra on these operators. When you can multiply operators, change order, introduce commutators. There is a lot what you can do with operators itself. If you compare this picture to classical physics, it's a whole new language you have to talk with. Absolutely different language. Before quantum mechanics, we never worked with operators. We never worked with wave functions like this. Well, maybe in some waves you have kind of wave function, but not operators. You never calculated expectation values like this. So maybe today we can start from this time-independent or stationary Schrödinger equation for finite square well potential. Yeah. Square well potential. I'm going to formulate the problem and we're going to solve it. And basically what we're trying to do, we're trying to find eigenvalues and eigenvectors of operator H. So as a result of this solution, you have to get a set of possible energies of my system and possible wave functions. What do I mean by square well potential? Well, I mean something like this. Let's say you have an energy as a function of x. It will be convenient for me to consider a symmetric potential. Minus L over 2, L over 2, and then your potential is 0 and 0. And inside this square well potential, just have something like this. So let's call this, how deep is my potential, is going to be minus V naught. And I'm going to have a particle inside with some energy E. So the particle will move from the left point to the right turning point and back. So classically, if it's a classical particle, and if particle is confined between these two walls, not infinite walls as before, but finite walls, it doesn't matter for classical particle. The particle will move from left to right and back, so the particle will be confined. The energy of classical particle can be any between 0 and minus V naught. If your particle will get more energy than 0, then it can just jump away and move to infinity from this potential well. This would be unbound state. I'm not interested in unbound states. I'm interested in bound states when particle is confined. So from classical physics point of view, I believe I understand very well what's going to happen to this particle. What about quantum mechanical problem? What kind of energies I may have in this system, and what will be the states, quantum mechanical states? So this would be a stationary Schrödinger equation which I have to write and solve. So this one, yeah. I assume that this is the states are going to have certain energy because it will be eigen function of operator of energy. Last time we did this already. So what we did before, before. That was infinite square well potential, so it was infinite. Remember? Infinite. So infinite. Well, for infinite square well potential, our energies were, okay, I have to recall this, but it should be pi square, n square, h bar square over 2ml square. So if you remember this correct, there was a ground state, and then the energy were increasing. And the wave function was like, if I try to plot my wave function, the first wave function was if you put half of wavelengths, then you put one wavelength, then you put two, and so on. So basically you were talking about standing waves, yeah? And one possible way to get these standing waves is just tell you that inside distance L, you can put integer number of wavelengths, of half of wavelengths, sorry. Yeah? So you can put either one half of wavelengths or two or three. This is very typical for standing wavelengths when you have two fixed ends. So now we can try to solve a more physical problem, because in reality you don't have infinite walls, you have finite walls. What's gonna happen? How can I solve Schrödinger equation for this kind of potential? Well, because it's 1D, it's not that bad, yeah? And I can show you how to do this. So let's start to formulate the problem. My Hamiltonian is p square over 2m plus potential energy. So I have to understand what is my kinetic energy, what is my potential energy. Kinetic energy is simple because momentum is minus I h bar d over dx. So momentum square would be minus h bar square second derivatives over x square. So this kind of gonna be operator. Basically, it's a second order derivatives over x. It's basically standard for Schrödinger equation. The second part, the potential energy. Well, I have to plug this realistic square well potential energy. So then potential energy, I would set something like this. If I incite this square well, then potential energy is minus V naught. So absolute value of x less than L over 2. So if I am inside between minus L over 2 to plus L over 2, my potential energy is minus V naught. And V naught is positive. So negative sign just reflects me that this is below 0. Then outside of my square well potential, what will be the potential energy if I go outside? It should be 0, yeah? Outside. So this what about the Hamiltonian. The second is, if I like to solve this equation, I also would like to put some restriction on energy. I don't want to consider positive energy because, as I mentioned, positive energy would mean unbound states, when particle can go to infinity. I would like to study bound states. So my energy will be less than 0, but not too much less, so I don't want to go below the potential energy. So then the second assumption of this preparation, my energy, it should be less than 0, but greater than minus V naught. Yeah? This would be the only restrictions I have. And basically that's it. The last condition is that my wave function should be bound, so I should be able to integrate it from minus to plus infinity, and I should be able to normalize it. That means the integral should exist. And also, my wave function should be continuous. Not wave function, and not even derivatives from this wave function over x should have jumps. Yeah? Jumps, or kind of discontinuities. This is an important condition, that there is no breaks or jumps in the wave function and the first derivatives of this wave function. Basically, this is a little bit less trivial, but I can maybe show later why my wave function should be continuous and the first derivatives should be continuous. So this slide prepares me to start solving Schrödinger equation. Maybe one more thing. Because I have symmetry, I'm going to borrow idea from the previous solution. I'm going to split my solution into symmetric, and antisymmetric. This can be proved that you can do this. So this is symmetric. You see the left side is the same as the right side. And it could be antisymmetric when the left side and the right side, they're different by negative sign. So whenever you have a symmetry like this, then you can always make your solution symmetric and antisymmetric. So it's going to help me to solve this problem a little bit faster and more efficient than just like without using symmetry. So let's write the equation then. Minus h bar square over 2m, the second derivatives over x. And this is my operator h, the first part, acting on wave function, plus potential energy applied to the wave function. So this left side is h acting on psi, and the right side should be eigenvalue and the same wave function. So this is the stationary Schrödinger equation. It's a second order differential equation with additional conditions like this. It should be integratable and it should be continuous, and the derivative should be continuous. What is my expectation from the solution? I actually expect to get a set of solutions. I expect to get allowed energies and allowed wave functions from this. So basically, I don't know energy and I don't know wave function. I will get both of them from this equation. And then we can try to make interpretation and we can try to play with the solutions. So then let's start. Let's try to write this equation in two different areas, inside and outside. So just let's see what's going to happen if my x magnitude greater than L over 2. What does it mean? It means that I'm going outside of the square wave potential. From classical physics point of view, I should not have a chance to be outside, yes? Because from classical physics point of view, I'm confined by the walls. But from quantum mechanics point of view, I'm still going to have an equation like this. What is my potential U outside of this square
Zero.
0.
Zero.
So then I can just forget about this part, yeah? Because I multiplied, my potential is 0. Then my equation is not going to be that complicated after this. By the way, when you put prime in physics, very often it's equivalent derivatives over x. So then second derivatives over x is double prime. When you put dots, it's a derivatives over time. Because people write it so many times, so they get lazy and they want to have some shortcuts. So let's remember that my energy is negative. This is important, that energy is negative. So this equation is equivalent that the second derivatives is minus 2me over h bar square psi. But my energy is negative. Remember, I'm below 0. So energy is less than 0. So then this coefficient is positive. You have negative sign and you have negative energy. So it would be convenient for me to say that, let's call this k square, something positive. So then if I make such notation, then my psi second derivatives would be equal k square psi. Okay, I tried my best to simplify the equation. So in this region, equation look like this. So what does it mean? You have to find a function. So when you take second derivatives from this function, you're going to get the same function with some k square coefficient. What is function? When you take derivatives, you get the same function. What kind of function is this? What could be possible solution for this?
Exponent function. And,
Exponent, yeah, you're
yeah.
right. We can say exponent kx, because if you take derivatives one time, k will go out. But then when you take derivatives second time, the second k will go out, yeah? So that's why you can get k squared. And it could be with any coefficient, just a constant. Or it could be another exponent, exponent minus kx. So when you take derivatives from the second exponent, you get minus k in front, yeah? But when you get another derivatives, you'll get another minus k. So you get minus k squared or k squared. So both of them will satisfy this equation. The equation is linear, and you have two constants of integration. So you can say it's a general solution of this. So this is interesting. My wave function outside of square wave potential is non-zero. It's a function of x. I don't know what is k because I don't know what energy is. I don't know parameters a and b. But I can say that outside, my wave function is a linear combination of these two. And I have to figure it out. What are these coefficients and what are this k? But k is related to energy. So if I can figure it out what is energy, I can tell you what kind of k is possible. So that was not that bad, yes? It's not the solution yet, we are coming, but that was nice. So this is interesting, this is solution below potential barrier. So if you go for x greater than L over 2 or less than minus L over 2, you are below potential energy. From classical physics point of view, you have no chance to go below potential energy. You have turning point, and then you go back. What if I incite the square wave potential? What will be the difference? I'd say magnitude of x is less than L over 2. Well, inside, my potential is a constant, yes? And this constant is non-zero constant. Now I can't just remove this term, I have to keep it. Well, whatever I have to write, yeah? So this would be my Schrödinger equation inside square well potential. So here I put minus V naught here. V naught is a constant because my potential is this constant. Yeah. Then I'm gonna do the same. I'll try to simplify this equation as much as I can. So I'll try to bring it to the standard form. Once it will have a standard form, then I can write a standard solution for this. So I'm gonna move minus V naught term to the right. I'm gonna multiply by 2m over h bar square and cancel negative sign, and I'm gonna get psi prime prime for this. Yeah. So let's see what I'm gonna have. Negative sign 2m over h bar square is probably the same. Energy is the same. Energy stays the same. This is the same, but I'm gonna have plus V naught here. So the only difference between inside and outside, this extra contribution from the potential. Yeah, there was minus 2me h bar square. This is minus 2me h bar square, my mistake, and V naught. Yeah, but there is something very different now. Before, this coefficient was positive. Yeah, because energy was negative. What about now? This coefficient is positive or negative?
will be negative.
The energy is negative, but V naught is positive. V naught plus energy, this combination, is going to be positive or negative? Just the brackets.
Positive.
Positive, positive. Remember, it makes sense to draw this again. So this is V naught, and this is my energy. So it's negative. My energy cannot be greater than V naught. So it's somewhere here. So then this combination is positive. So the total coefficient would be negative. It makes big difference because previously this coefficient was positive. Now, when you have a classically allowed area, when energy is greater than potential energy, so this would be negative. Okay, it's not a big deal, but still. I'm going to introduce kappa square for this combination. So not k, kappa. So this combination would be positive. That's why I call this kappa square. Otherwise, I could not do this. And I can rewrite this equation for inside as second derivatives over x equals minus kappa square psi. So there are two differences between this equation and previous. One difference is the sign. There was positive sign, now it's negative. The second difference is the coefficient itself. The first coefficient was just minus energy, it was positive. The second coefficient is energy plus V naught. It's also positive, but it's different. Yes, it's shifted by the depths of the potential. But it's not a big deal, yeah? I can solve this. This equation looks very similar to this one. But solution will be different. What kind of function is, if you take second derivatives, you get the same function with negative sign. This negative sign now start to play important role. You take second derivative, sine and cosine, yeah.
Yeah.
So then, instead of having exponents like this, my solution would be harmonic functions. So the solution would be some coefficients. I'm gonna pick just different coefficients, maybe A, B, C, like cos, kappa, x. So I'll try to make difference between kappa and x so you can distinguish them. Or maybe sine, kappa, x. So what do I know, what I don't know in this solution? Well, apparently coefficients C and D, they can be any. It's a general solution, yeah? Kappa I don't know because kappa depends on energy. And energy, we don't know energy. Now, but technically, I solve the problem. My wave function would be equal two different functions outside for x greater than L over 2 and inside. This is a solution of the Schrödinger equation. It's not solution yet, but it's solution of the differential equation, yeah, the general solution. Then I have to look back what kind of conditions I have on this solution. So basically what I did, I solved the first part. This is a big one. And I satisfy this condition that my energy is less than 0, but greater than minus V naught. So what I have to do now is just make sure that these guys, these conditions are satisfied. My function should be integratable because it's bound state and I would like to normalize it. And my function should not have jumps, it should be continuous. I should not have any discontinuity in my wave function. So, and it looks like I can satisfy just this condition. After I satisfy them, this would be the solution, and that's it. It's not that simple yet. We are coming to this, but okay, let's think about it. So let's speak about solutions which are symmetric and anti-symmetric, or odd even solutions. Odd even solutions. So if you take psi minus x, you can get either the same. So this would be like my cos function or like this function. So it's a symmetric solutions. Remember from standing waves. Or you can get negative sign. So for example, this one. If I flip it, then I'm gonna get negative sign. So one would be symmetric, or second would be anti-symmetric, or one I can call even function, and second I can call odd function. So then let's try to split solution into two, separately even and separately odd solutions. So for example, even solution. It's a small trick, but this trick kind of helped me to save maybe twice as much time. For even solution, I have to care only about one side of the solution, because the second side will be just a reflection. It's a symmetric function. Yeah? If I know this part, I can easily find the another side. I'm going to keep this in mind. So then my wave function for symmetric or for even solutions would be equal. So let's say for x equal greater than L over 2, very large x. For very large x, what kind of wave function you would pick? A term, B term, or both of them, A and B? What happens to A term when I go to infinity? If x is very large, what happens to the A term?
It also goes infinity.
It goes to infinity.
Yeah.
What happens to B term if I go to infinity?
It goes to 0.
It goes to 0. Can I keep both of them? I'm thinking about that my wave function I should be able to integrate it. If my wave function goes to infinity,
No, you cannot, because it normalizes one.
there is no way to integrate it, yes? It's not normalizable. Such wave function is called unphysical. It doesn't represent me bound state. It's a serious restriction for me. It looks like it's a very simple condition that I should be able to integrate this wave function. But actually, it's a serious restriction. If you keep this in mind, then which of these terms you would keep for large x?
By one.
Only second one, B term, yeah? Then what if you're inside the potential well? And you're talking about even functions, which are symmetric functions. Can you keep both of these terms or you keep only one?
No, it has to be the first one.
The first one, because cos function is even function, yes? Then the sine function you would keep for the second type of solution, for anti-symmetric solution. So then it was coefficient C cos kappa x. And then maybe for x less than L over 2, this would be something on the left side. I would pick the same coefficient B because it should be symmetric. But my exponent should go to 0 when x goes to the negative infinity. So which of these two you would keep for large and negative values? I would keep the first one. Because when you go to a large and negative x, this would be small. So then I could reduce some constants, yeah? Instead of having 6 constants, I have only 2, B and C. And I have energy. So what I still don't know, I don't know B, I don't know C, and I don't know energy, meaning that I don't know K and kappa. So these are unknown. But I can build a symmetric solution from this. For example, from left side, I'm going to have an exponent.
So the limit has, the frontier has to have the same value.
Yeah, it should be symmetric, yeah?
No, but I mean, the same value even with the one in the middle, right? They are continuous.
Same value where?
At the frontier of the regions, the central one and the one on the right of the
Oh,
left.
you mean there should not be jumps, it should be continuous. Yeah, when you approach this well potential, you approach it by exponents. But then inside, you have cost function.
Professor,
Yeah,
the third one shouldn't be x less than negative L over 2?
yes,
Yeah, okay.
thank you. So then inside I have cost function, outside I have exponents. So let's try to think about what conditions I can satisfy by doing this. First of all, I pick symmetric solution. This is important for me. Then I can guarantee that this equation will be satisfied because I can integrate it. When you have exponents which goes to 0 at infinities, then I have no problem with the normalization. Then I have two more conditions left. My wave function shouldn't jump, and then the first derivatives of the wave function shouldn't jump as well. Then I have to just look what happens at the borders, because if you have a border, let's say L over 2, if your x is greater than L over 2, then you have a exponent, and if your x is less than L over 2, you have a cost function. I have to connect them because I don't want to have discontinuity. I would like to have a smooth function. So then the coefficient b and c should be adjusted in such a way that I have no jumps, I have no discontinuities. And if I can do this at one point, like L over 2, the other point, x L minus L over 2, will be done by default because it's a symmetric solution, yeah? Your left side is a reflection of your right side. So I have to do this only on one side. So then I have to be now careful about which constants I can pick. So I have how many conditions? Two. My wave function should be continuous and the derivatives of my wave function should be continuous. How many equations, how many unknowns I have? I have three unknowns, yeah? And I have two conditions. Well, I have also normalization condition. So maybe all these three conditions would be enough to find energy and constant B and C. But also remember, I have to get many solutions. I have to get all possible energies and wave functions. So then somehow, when I write this condition for connection, this two wave functions, I'm gonna get more than one solution. Well, let's see. Let's see what's gonna happen. So I'm gonna write it down. I'm gonna say that wave function. Okay, let me write it nicer. The wave function at point L over 2, when you just approach from positive, from the right side, yes, plus 0, it's gonna be what? Coefficient b exponent minus k L over 2, yeah? This is the value of my wave function at L over 2 if I approach this from the right side. So when I approach this from the right side, I'm gonna pick this one. And this should be equal to the wave function at L over 2 if I approach this from the left side. So it's going to be C cos kappa L over 2. So this kind of condition. So it tells me that coefficients B and C should be related somehow. Yeah, I should adjust B and C in such a way so then when you approach L over 2, you come to the same point. Well, I hope this makes sense. Sometimes people introduce a difference between this as a jump. And that this jump at L over 2 should be 0. Your wave function must be continuous. So this is a condition. And I have another condition that the first derivatives of my wave function at L over 2 psi prime L over 2 plus 0 minus psi prime L over 2 minus 0, that the first derivatives of my wave function should be continuous. So then I have to be careful a little bit. I have to take first derivatives from this and then plug x equal L over 2. Yeah. What's going to happen if I take derivatives? I guess minus k coefficient will go in front. Yeah. So instead of this, I'm going to have minus k b an exponent. This is the first derivatives at L over 2. If I approach L over 2 from the right side. What about this guy? If I take derivatives and then approach x equal L over 2, what I'm gonna get?
Negative kappa C psi
Psi
kappa x.
kappa x, but then you approach L over 2. Okay, sounds good enough to me. Then let me write one equation below another. So these are the last two equations which I have to satisfy plus the normalization. Yeah, looks nice. I don't know B, I don't know C, I don't know K and kappa because they depend on energy, which I don't know. Interesting. What I can do from here, maybe I can divide left side by left side, right side by right side. In this case, I'm going to cancel B and C. And I'm going to get equation only for energy. This is a little bit non-trivial, but if you can see this, it would be nice. So what if I take left side and divide it by the left side? Right side, and I'm going to divide it by the right side. Can you see that coefficient B will cancel out? This exponent will cancel out. Yeah. On the right side, the coefficient C will cancel out. Sine over cos, unfortunately, doesn't cancel. It's going to be tangent. Okay, so I have to write it, yeah, because this would be my equation for energy. So minus K, is it minus K? Because B cancel out, this guy
Yes.
cancel out, so minus K equals to minus kappa tangent, and then you have something like a kappa L over 2. That's an interesting equation. I have to do something about this equation, but apparently I can either satisfy this equation or not. If I satisfy this equation, then I will find continuous solution. How can I satisfy it? Well, I can adjust energy, yeah? My k square was equal to negative 2me over h bar square, and my kappa square was equal to 2m h bar square. Was it like e plus v naught? Yeah. So apparently I can try to change energy. If I start to change energy and then I don't have solution, I don't have solution, I don't have solution, but maybe at some magic energy, suddenly I can solve this. So then will be some very specific energy for which this equation will be satisfied. And then I can satisfy this equation which makes it continuous. I can relate B and C. So instead of B and C, I have only one coefficient left. And then I can apply normalization condition. So I can adjust the last coefficient by normalizing my wave function. So it seems like this is the light at the end of the tunnel. I can solve this equation to find energy. Once I know energy, I know K and kappa. I can relate coefficients B and C, so I can get rid one of them and have only another left. And then I just normalize my wave function. So I can find the second coefficient. So this sounds as a plan. The only what I have to do is to solve this equation for energy. And this would be kind of a challenge, yeah? Let me rewrite this somehow and simplify it as much as I can. Tangent of kappa L over 2 would be equal K over kappa, yeah? And this is the best way how I can simplify it. Okay, I can probably plug K and kappa here. I don't see much of the sense of doing this, but that's possible, yeah? I'm gonna do a little bit different trick. I'm gonna label somehow this argument of my tangent. So whatever you like. Kappa L over 2, let's give it a name. Whatever, some Greek letter. Xi. Xi is hard to write, so you can write something like mu. Or whatever. Let's pick Xi, doesn't matter. Then I can try to look what I have here. I have KL over 2 over kappa L over 2. This is going to be Xi, and this is going to be Xi. And the numerator, I can try to express as a function of Xi. What I'm trying to do, I'm trying to make it as simple form as I can. So my goal is to write something like this. Tangent of its argument, which I call Xi, would be equal some numerator over Xi. And then I'm going to write down the numerator and I'll try to solve this equation somehow. Okay, so numerator, KL over 2. Let's look at this K and kappa and how they're related. K square L square over 4. Let's form this combination because this is what I actually want. would be equal minus, and just try to make sure that I don't make mistakes. 2m L square energy for h bar square, yeah. I just multiply it by L square over 4. And I'll do the same here. L square kappa square over 4 would be equal positive 2m L square energy plus V naught L square over 4, yeah, 4h bar square. So I'll try to compare them, and what I'm gonna see that the part with energy is identical. Can you see that this part with energy, they are similar? Keeping this in mind, I can say that this guy would be equal minus L square kappa square over 4, because it's a minus this part. But when you subtract it, you also have V naught part, which you have to remove. Plus 2m L square V naught over 4 h bar square. So this would be a nice relationship for me. Check it at home. It should be clear that this energy can be related to this guy minus V naught term, because they are the same. But it will help me to find the numerator. My numerator then would be minus xc square. This is xc square, yeah? Plus something. I'm gonna call this for simplicity xc naught square. So where xc naught square is this combination. Basically xc naught square is V naught. And finally I can find the numerator. Lk over 2 would be square root from xc naught square minus xc square. So a lot of work just to get my equation look a little bit more nicer. Tangent of xc equals square root xc naught square minus xc square over xc. And I have to find solution of this equation. I can tell you from the very beginning, it's not possible to find solution of this equation. It's a little bit nasty. We can analyze this. Oops, wrong color. By analyzing, we can conclude something about solutions. I'm not going to really jump and analyze it right now. I want first to come back and do the same for anti-symmetric part. But now, after we did all of this hard work, it will be much easier to do anti-symmetric part. That was symmetric. Symmetric or even solution. What would be the difference for anti-symmetric or odd solutions? What should I say? For the middle part, if you're looking for odd solution, anti-symmetric, for the middle part, what would you pick?
Sine.
Sine. Then for x greater than L over 2, you still can keep only one exponent. Yeah. For x less than minus L over 2, you just put a negative sign here because it's anti-symmetric. But the only difference would be you change cos to sine. and that's it. So odd solution. Now if you let me, I can go a little bit faster. So my wave function would be b exponent minus kx, then d coefficient sine kappa x, and then minus b, it should be plus, yeah? Plus kx. Then the jump of my wave function at L over 2 must be 0. What kind of conditions I'm gonna have? B exponent minus k L over 2 must be equal d sine kappa L over 2, yeah? The wave function from both sides at L over 2, I must have the same value, sine, yeah? What about the continuity of Lx prime? What condition I'm gonna have? From this side, you take derivatives, yes? Minus k go in front.
So minus KB E exponent negative K L over 2
Beautiful. Equal to
equal
what?
to kappa D cosine
Kappa d cosine.
kappa L over 2.
I'm gonna use the same trick. I'm gonna take the ratio. Left side over left side, right side over right side. So then on the left side, I'm gonna get minus 1 over k, yeah, because you take this over this. And on the right side, d will cancel out, it will be 1 over kappa and tangent, yeah. So then for anti-symmetric solution, tangent kappa L over 2 must be equal to negative kappa over k. And this is different from previous one. Previously it was k over kappa, positive, k over kappa. Now I have kappa over k negative. It's not a big difference, but it's different, yeah? So then let me conclude. So I have symmetric and anti-symmetric. Symmetric. Then I have a tangent of some parameter xi equals square root xi naught square minus xi square over xi. And I have anti-symmetric. Then I have the same tangent of the same kappa. So basically I have to flip it. So when I flip it, I have a xi over square root xi naught square minus xi square, yeah? But negative. So whatever energy I find on my left side, this would be energy of symmetric solutions. Whatever energy I can find on the right side, this would be energy of anti-symmetric solutions or odd functions. So now once I have both of them written, I can show you how to solve this equation, but in reality you can't really solve this. It's a kind of unsolvable equation. We can try to do this graphically. We can plot this function as a function of xi and the right side function as a function of xi. And we can just try to see what these two functions equal each other. Parameter xi, it would be interesting how parameter xi changes. What was the definition of xi? This is my xi. This is basically xi square, yeah? Then let's analyze the range for xi square. So xi square equals, one more time, 2ml square, yeah? Then energy plus V naught over what? Over 4h bar square. The energy changes, so my parameter xi is gonna change. What can be the smallest value for xi? I can move energy down and make it as small as possible. What is the smallest energy I can have? Remember, what was the lowest energy? You can imagine this square well potential. The smallest energy equal negative V naught. You can go deeper than negative V naught. Then what will be the smallest xi?
0.
0. So then my xi must be greater than 0 or equal. Okay, when you go up in terms of energy, how high you can go? What is the maximum energy we agree to consider?
0.
0. So if you plug 0 and you look at this with attention, you will notice that this is my xi naught square. So then the maximum possible xi is xi naught. And this is very good because if I have xi greater than xi naught, I have a negative value under square root, which could be a problem for me. I don't want to go higher than xi naught. I'm just going to be confined between 0 and this parameter. Whew, that was kind of a hard work for me. So now the best part, I guess. So let's try to draw functions, the left side and the right side. So tangent xi. Tangent is 0 at 0, at pi, at 2 pi, yeah, and so on. Tangent is infinite at pi over 2, yeah, at 3 pi over 2, and so on. So then my tangent function look like this. And actually more. Then if you go down, okay, let's agree on this point. This is 0, this is pi over 2, yeah, 90 degree. This is pi, this is 3 pi over 2, this is 2 pi, maybe 5 pi over 2, 3 pi, and so on. This is a typical graph for tangent, and you would agree with this, yeah? What about this function? Let's look at the symmetric solutions. So function like this. First of all, this function is going to be 0 around xi naught. So if you have somewhere xi naught, then this function is 0. This function is positive. well, if xi is less than xi naught, but the function doesn't exist if xi is greater than xi naught. I don't want to go to the greater points. I want to go to the smaller xi. But I cannot exceed this value, yeah? Xi naught. And I know that if I reach xi naught, this is going to be 0. Well, when I have a very small xi, what would be the value of this function if xi goes to 0? Numerator will be constant, denominator will be very small. What will be the asymptotic behavior? It will go to infinity and positive infinity.
Yeah.
So then if I reach very small values, then I'm going to be at positive infinity. And then we have to connect these two asymptotic behaviors. From very small xi, when my right side is infinite, to xi around xi naught, when my right side is 0. So I'm going to draw something like this for you. So where is going to be my solutions then? The solutions would be when you have intersection. Yeah? Very interesting. I'm going to have finite number of solutions, not infinite, finite. And how many solutions I'm going to have is going to depend on my parameter xi naught. The parameter xi naught becomes very important. What if I have very small parameter xi naught? How many solutions I'm going to have if my xi naught is very small?
Maybe just one.
Just one, yes? What if my parameter xi naught goes to infinity? What if it's a very large parameter? I'm going to have a lot of solutions, yes?
Mhm.
What does this parameter mean again? It seems like the parameter is very important for me because it basically controls how many energies I can have in this square well potential well. So I'm going to go back and write this xi naught. So this is basically, where it is xi naught, xi naught. Okay, this is the definition of my xi naught. This is not xi naught, it's a xi naught square, so I have to take a square root of this. Okay, I can take square root. I don't have a problem taking square root of this. 2ml square v naught 4h bar square. Okay, let's write it down. So parameter xi naught is the square root of 2ml square v naught over 4h bar square, yeah? So basically parameter xi naught is how deep is my potential v naught, yeah? If I make it very deep, so if v naught goes to infinity, that would be a very, very deep potential well. Then xi naught will go to infinity as well, yes?
Mhm.
And then number of solutions.
Okay. Infinity.
What if my parameter v naught goes to 0? Then xi naught goes to 0, and then I have number of solutions.
Okay.
Surprisingly, I will always have one solution, always. No matter how small is this parameter xi naught. If it's very small,
Yeah.
I'm still going to have intersection no matter what, yeah? It's interesting. But this is not the end of the story. I have anti-symmetric solutions. This was symmetric solutions, yes? What about anti-symmetric solutions? Well, this was symmetric. For anti-symmetric, I have slightly different function. First of all, it's negative. It starts at 0, and then it goes to infinity at when you reach xc equal xc naught. So then I have to analyze this function a little bit more. So I'm going to write it maybe different color. So negative xc over xc naught square minus xc square. It's anti-symmetric, and this is symmetric. So it's negative. So you start from 0. When x equals 0, it's 0. And it's negative. And when I reach x naught, my numerator will be 0. So I'm going to reach infinity. So then these guys should connect like this, maybe. I slightly change it. Okay, if you let me into this one. This would be anti-symmetric solution, and I have solutions as well, yeah? So if parameter x naught goes to infinity, I will have many solutions anti-symmetric as well, yeah? But what if my parameter x naught goes to 0 or to very small values? How many solutions, how many anti-symmetric solutions I'm going to have?
0.
0. So if my x naught will be somewhere here, then it will go to infinity. And I don't have intersection, yeah? So there will be no solutions, anti-symmetric. So we can conclude a couple of interesting facts. When you have a very shallow square well potential, so if V naught goes to 0, so it's very shallow square well potential, then you always have one symmetric solution. Always have one symmetric solution. So now I have some time left. I would like to talk about quantum tunneling. And I would like to draw wave functions and solutions for this a little bit. And I hope that 40 minutes would be enough for me. So first of all, let's find the solutions for these intersections when you have a very large xc naught. Apparently, you can't find solution in arbitrary case. Maybe only graphically, or maybe a computer program can do this. But in the limit, I can. So if xc naught goes to infinity, so it's a very deep well, yeah, deep well. That means that your V naught goes to infinity. Can you guess if this parameter goes to this point, if it goes to infinity, where this intersection are going to be? Close to what point? Just try to move this to infinity. Where this intersection happens?
Close to the x axis.
Close to what
Pi
point?
2,
Oh.
pi over 2, 3 has
Pi over 2, 3 pi over 2, and so on. These are for symmetric solutions, yes? What about anti-symmetric? If this point goes to infinity, where are going to be intersections?
Pi, 2 pi, 3 pi?
Away
Yeah,
from
yeah, pi, 2 pi, 3 pi. So then we can say, in this limit, my xc, the solution, it's not going to be exact. It's only be exact in the limit. But my xc, no, sorry, I want to switch color to normal. My xc approximately would be equal pi over 2 or pi or 3 pi over 2 or so on, yeah? This would be symmetric solution, anti-symmetric, symmetric, anti-symmetric. This would be approximate, yeah, because it's a limit. This makes sense. Can I write it like this? Xi anti would be equal pi over 2 multiplied by some integer number. Maybe. Does it make sense or not? This would be n equal 1, n equal 2, n equal 3. Does it make sense? Integer number of pi over 2. Pi over 2, pi, 3 pi over 2. Yeah? Okay, approximately. You agree with this? Parameter Xi was kappa L over 2. And parameter kappa was related to energy. So kappa square L square over 4 equals pi square 4 n square. And this parameter kappa, can you remind me what was the kappa? I did it somewhere, yeah? Here, L square kappa square over 4, this combination. I have to bring it back to that slide. Okay, I'll try to do this, but try to correct me and check me. So this is a 2m L square energy plus V naught over 4 h bar square. This is my kappa square L square over 4, yeah? Must be equal pi square 4 n square. Yes or no?
Yes.
Right.
This is a solution, approximate solution of my equation for symmetric and anti-symmetric, symmetric, anti-symmetric, symmetric, anti-symmetric. And in the limit, when you have a very deep square well potential. Then my goal is to find energy. I can cancel 4, and that's it. I can't do more than this. Then I can find energy plus V naught. Energy plus V naught would be, if I multiply it by h bar square, pi square, n square, h bar square over 2m L square. Can you recognize this equation? The only difference is between this solution and infinite square well potential is the initial constant. I count my energy not from 0, but from minus V naught. But then on top of this minus V naught, this is the same solution as we had before for square well potential. Does it make sense? Remember this. This is your solution for infinite square well potential. So that means if you have a very deep square well potential, then your energy spectrum at this level would be the same. The only difference that you start not from 0, you start from minus V naught. You have this minus V naught, and on top of this, you have these levels. Your wave function would be slightly different now. So your wave function would be like this. So before it was a half of wavelength. Yeah. Now you will have slightly different behavior. You have a part of the cos function, like the cos but then you have this exponential tail. So what you have in between is cos kappa x, yeah? What you have outside is the exponent. So this is the exponent minus kx. This is exponent kx, and this part of the cos function, kappa x. This solution will be smooth. So I have no discontinuity here on the border lines, not for the wave function, not for the first derivatives. Before, it was just zero because it was infinite. Now I have these probabilities. I can go into forbidden area. And this will be n equal 1 solution. What about n equal 2? N equal 2 would be anti-symmetric solution, yeah? Then anti-symmetric solution is a sine function. And then you have exponent. So the exponent would be here. Then you have part of the sine function. And then you have a here. But I get almost identical spectrum for this one. This is very interesting. And I would like to show you solution for another limit when your parameter xi naught is very small. In this case, you're going to have only one solution, and this would be symmetric solution. This solution is remarkable to some extent. And you even can find energy approximately of this solution. That's not that hard. But this solution opens a little bit eyes on what we call the tunneling, quantum tunneling. And basically both of these solutions are related to quantum tunneling. And simply quantum tunneling is based on these exponential tails. See these exponential tails? This means that you have probability to get into classically forbidden area. So if parameter xi naught is going to zero, and also the solution will go to zero, then in this case energy will go to zero as well, because both of them are going to zero. I don't know if it's obvious or not, but I believe somewhere we should have it. Yeah, this is your energy. So you basically energy equals to xi naught square minus xi square. Both of them are very small. So then k is going to be very small, and the energy will be very small. When you have such a small energy, this is going to be a shallow potential well and shallow energy level. So you have a potential well, which is kind of shallow. Maybe I'll try to do this better. Yes. And your energy level is very close to zero. All of them are close to zero. What's going to happen in this case? That your wave function will be localized at very large distances. So it's going to have a very long exponential tails. What does it mean? it means that you can find particle here and you can find particle here. Somewhere where you cannot find it from classical physics point of view. So these exponential tails will give you probability of finding your particle outside of classically allowed area. So we can find the particle here. So the only problem is these exponential tails, how fast they are going. So these exponential tails is a proportional exponent minus kx, yeah? These are exponential tails. These guys, they're supposed to make probability to go beyond this potential well very, very small. But we know the parameter k. The parameter k can be related to square root of 2m minus e over h bar square, yeah? This is my parameter k. So then the exponent will be minus square root. Actually, I can remove Planck constant from the square root. I don't know if it's gonna be better or not. 2m minus e. Energy is negative, that's why minus e is positive. X over L. This coefficient can be either small or large. And this is my probability to find my particle somewhere outside of this square well potential. Remember, from classical physics point of view, this is not allowed. In quantum mechanics, we're going to have this probability, but this probability, well, maybe you have to make it square and integrate. So if you make it square, probably you have to double this, yeah? But I don't really want to talk about these coefficients. It's not that important. From classical mechanics point of view, there is always a chance to find particle outside of your potential well. How does it bring quantum tunneling? It's actually now it's very simple. Let's say you have a potential well and you have ground state. And ground state would mean that you have a part of the cost function and you have exponential tails, yeah? What if you have another potential well at some distance d? So energy. From classical physics point of view, what's gonna happen? Well, particle is gonna move from left to right, right to left, and particle can never make it through the barrier, yeah? There is no chance in classical physics. What about quantum physics? Well, you have this exponential tail, yes? So then there is a chance to find particle here, isn't it? Because you have your wave function decay this exponentially, you always have a chance to find it far enough from your potential well. So if particle was here, you have a chance to find it here. Particle can tunnel through. It can be here. So then you can go through the barrier, through the potential barrier. Of course, it's going to depend on your energy. If you go deep inside, then it's going to be harder. The potential barrier will be greater. It will be harder for you to tunnel through. Of course, it should depend on the distance you have to tunnel through. But first of all, there is always a chance. So, for example, if I will try to, let's say you have a wall, and I'm trying to run. Can I tunnel through?
No.
We can estimate it right now, yes, because we know probability. Probability for a classical object to overcome, to go through this potential barrier. For me, it's a potential barrier, yeah? Normally, I would just reflect. The probability would be minus 2 square root of 2m my energy. I put magnitude value. So the energy required to go out of this potential barrier, h bar, and maybe the parameter x. I'm going to replace it with distance. So then we can try to see what if my m is 1 kilogram. Let's say it's not me, just 1 kilogram ball. The energy is roughly 1 joule, and the distance I have to move through is 1 meter. So I'm picking a typical macroscopic classical object. So a 1 kilogram ball should tunnel through 1 joule potential barrier over 1 meter distance. From quantum mechanical point of view, what will be the chance that this is happening? Then we can say, okay, no problem. We can estimate probability of this happening because we kind of understand how this tunneling happens. It happens through these exponential tails of my wave functions. And these are my exponential tails. Let's plug the numbers. Exponent minus factor 2, square root of 2, 1 kg, 1 joule, 1 meter, yeah? All numbers are 1, 1, 1, and Planck constant here. What was the Planck constant? 1.0555 or 53, 10 to minus 34, yeah? What I'm gonna have in the numerator, or in this exponent? Negative what? Forget about constants. Just calculate power of 10. What is the power of 10 of this?
34.
10 to power
34 or something.
So the probability would be 1 over exponent 10 to 34. I don't know if I can understand how small is this number. It's not 1 over 10 to power 34. It's 1 over exponent 10 to power 34. I don't know how to explain this. This is what we call zero in physics, yeah? If you have just 1 over 10 to power 34, this is already very small chance. But you have an exponent in this power. I don't know if you can feel it or not. Can you feel this? This is extremely small. This is zero. It's the official definition of zero. Of course, you can try many times of doing this. If you can try it that many times, maybe out of this many times will be successful, who knows. But this number is unbelievable. So then for classical objects, for macroscopic objects, we can actually forget about tunneling. Yeah. And why we can forget about it? Because of this Planck constant. The Planck constant will make these exponents dying extremely fast. If you want to compensate this small Planck constant, what you can do, you consider a very small distance. So of course, if your distance, 10 to minus 34 meters, you can tunnel through this, yeah? Because the small distance will compensate small Planck constant. But what is this? It's a significantly less than the size of a quark or proton and neutron inside nucleus. The size of proton and neutrons is 10 to minus 15 meters. Yeah, 10 to minus 15. So who wants to tunnel through this distance? Yeah, it makes no sense. So Planck constant plays a very significant role because it basically makes our classical world, classical laws of nature, valid for classical objects. But we can consider something like an electron. For example, let's say you have a hydrogen atom, and I'm going to model hydrogen by a square well potential. So my electron is going to be bound in this square well potential because of proton. Yeah, the proton will create square well potential. Electron is bound. This is a very kind of rough model of hydrogen atom. I'm going to bring another hydrogen atom next to it. Another hydrogen. So then my question would be, is it possible for electron to tunnel through and get into potential well of the second hydrogen atom? What would be the probability for electron to tunnel through? And if it's possible, then let's say you have two electrons which can go left and right and can tunnel through. They can combine these two hydrogen into H2, yeah? So for the electron, the typical height of this potential barrier energy, it's about 13.6 electron volt. Yeah, it's a binding energy in hydrogen atom. This would be the height of the potential barrier. The distance, so let's assume it's a typical atomic distance, yeah, 10 to minus 10 meters. Then distance energy, what else? The mass. The mass of electron is 911, 10 to minus 31 kg. What else do I need to estimate the probability? I need m, energy, distance, and Planck constant. I believe I'm fine, yeah? So what would be the probability for electron to jump through this potential barrier from one hydrogen atom to another hydrogen atom? If hydrogen atoms are close enough, binding energy is given, the mass of the electron is given. Let's estimate it. We're still gonna have Planck constant, of course, but now the numbers are different. And I have to change energy to joules because it's all standard units. So 1 electron volt is 1.6 10 to minus 19 joules. So the probability would be factor 2 twice 911 10 to minus 31 13.6 electron volts 13.6 1.6 10 to minus 19 distance Bohr radius, and then you divide it by it's very scary Planck constant. So the all units are standard units in international system. So kilograms, joules, meters, and Planck constants. Okay, can you help me? Let's move powers of 10. 31 and 19. What is going to be total? Minus 31 and minus 19. Is it 50? Yeah. Minus 31 minus 19. 50, yeah? What will be square root of 10 to minus 50?
25.
Negative 25, yeah? And you have negative 10. And you have denominator.
That's bad.
They cancel out each other. Look at this. Can you believe this? That is carried 10 to minus 34, which killed probability last time. Now it's gonna vanish. Because you have distance 10 to minus 10, you have m 10 to minus 31, and you have energy 10 to minus 19. Oof. I'm gonna get 10 to minus 1, yeah? What about the rest? If you can, okay, I can do maybe factor 2 and 0.5. This is just 1. This one I can neglect. It's 1. So what I have left is 2, 9, 13, and 1.6. Can you help me? Can you just multiply these numbers and take a square root from this? 2, 9, 11, 13.6, and 1.6. My expectation that this would be like close to factor, I don't know, 10 or 20. So there shouldn't be a big deal about it.
I got 0.50. I'm not sure.
For everything,
Yeah,
or only for square root?
for everything.
For everything.
Yeah.
Minus 0.15, yeah?
I mean, for the exponent is also get 0.50. I mean,
Oh,
include,
everything.
yeah, everything.
But it's like it is not a very small chance, yes? Then it's gonna depend how many times electron can hit this wall. So if electron goes left and right, then it's gonna hit this barrier many times per second. And every time you have certain probability to tunnel. So at some point it can happen. We are talking about reasonable numbers. This can happen, yeah, the tunneling. It seems like this equation for exponential tails does not let classical macroscopic objects to tunnel through anything. But it's very fine and forgiving for elementary particles in atoms like electrons. So basically, this is what we can learn from this solution. So then maybe just describe it one more time. So if you have a square well potential of finite width, finite height, then you will always have several levels. Minimum, if you have a shallow square well potential, you always have at least one level. If you have a deep square well potential, then you have more levels. But even if you make V naught very small, you're gonna always have at least one level from this. So then you have some energy levels, and you can build what's called binding states, stationary states. And the ground state will look like you have a part of cos function, and you have these exponential tails, which can bring you to classically forbidden area. Then the next level would be sine function. And the next level, maybe if I can just pick a different color, it's going to be symmetric and like this. And then you can move further and further and further. Yeah. Maybe last semester, Tsai Wu was trying to find these solutions through a computer program.
Yes, right.
So now you can recognize a little bit more. So alternative way to computer program would be still a computational project to solve these equations and find the solutions on these equations. Yeah. So you see, we found many solutions as I promised you. So we have a possible values for energy, and we have a possible quantum mechanical states like this. And we have these exponential tails which teach us about possibility of tunneling. So all these solutions came from Schrödinger equation. Hamiltonian applied to wave function, I must get the same function and some constant, which we call energy. I'm gonna finish by talking about alpha particles and alpha decay. So alpha particle is a helium-4 nucleus. It's a combination of 2 protons and 2 neutrons. Proton, proton, neutron, neutron. It's a very stable combination of protons and neutrons, yeah, alpha particles. When you speak about alpha decay, that means a nucleus will eject an alpha particle from this. So then if you have a nucleus with a mass number A and Z number Z, then when you have an alpha decay, then you're going to get another nucleus with A minus 4, because you lose 4 particles and you lose 2 protons, alpha particle. I'm going to show you one way how we can construct a model which can describe this alpha decay based on quantum tunneling. So we can introduce nuclear potential for alpha particles as a function of distance potential. And typically potential looks something like this. So this normal square well potential, but then you have this Coulomb repulsion. So it's a little bit complicated, maybe potential energy. So if your alpha particles has a level here, there is no way to escape, yes? because you can never reach infinity. You always will be below the potential energy. But sometimes this would be stable nucleus. But sometimes you have level here. And because you have a potential barrier, it's not easy to escape for particle. So then the alpha particle is moving left, right, so it's confined in this potential well. But every time you hit this wall, you have a chance to tunnel. And in principle, that's possible. So eventually, this alpha particle will escape because the wave function allows to go under this potential barrier. So you have a probability to tunnel through, but probability will depend on parameters like how wide is your potential barrier and how much energy do you need to overcome this. So basically you can use the similar estimation like this for the tunneling. Maybe you can be more accurate, maybe you can be less accurate, but so you have probability to tunnel. And then you have a frequency, how many times per second this alpha particle hits this barrier. And this is what can be probability per unit of time. Because you have many attempts. If probability is small, but what if your frequency is 1000 hertz? So then you do these attempts 1000 times per second. So eventually this alpha particle will escape. And if this was a nucleus, the nucleus is going to lose this alpha particle. So, and we can estimate the probability per unit of time, and probability of unit of time can be related to what's called lifetime constant, or lifetime of this radioactive decay. Probability of tunneling can be related to this exponent, and frequency can be just calculated if you know energy and the size. And this was done. It's relatively simple. It's a very elegant and nice problem. But this explains you the mechanism of radioactive decay. If you have a particle confined like this, the particle does not escape immediately. It will need some time before escaping. So this is a lifetime constant. Can be very small. Let's say, I don't know, 10 to minus 6 seconds, microseconds. Then this radioactive material will decay very fast. So in microseconds, you're going to lose half of this material. But this time constant can be 1 year or 6,000 years. So then the large time means small probability. Small probability, maybe barrier is too high, or maybe frequency is too low, or maybe a combination of this. But small probability means longer lifetime for this radioactive decay. So it could be thousands of years before this alpha particle will escape. So this is a little bit of physics behind radioactivity. It's a tunneling through the barrier. This is actually what happens in real life. So this is not just impossible things. But of course, it should be applied to microscopic particles, like electron or alpha particles. Not for this poor guy. I believe I'm done for today. Do you have questions?